All right, we are live. And Dan, I will hand it over to you to do the introduction.
Thanks, Spiro. It's my pleasure today to introduce Dr. Dharmendra Arumugam. Dharman is a senior research technologist at JPL with interest in atomic sensors for remote sensing, applied physics, and sensors. And he's also the group supervisor for the Concepts and Formulation Group in Section 334 at JPL. He received his PhD from Carnegie Mellon. He's received a number of awards. Some of them include NASA's 2015 Lou Allen Award for Excellence for inventing and developing active and passive magnetoquasistatic positioning for long-range near-field positioning for non-line of sight environments. He's also, he was named by Popular Mechanics in 2017 one of the top 10 breakthroughs of the year for his precision outdoor and indoor navigation and tracking for emergency responders, or POINTER project. He also brought about a collaboration between the Department of Homeland Security and NASA using POINTER to help locate firefighters when GPS can't penetrate. And he also recently is the recipient of NASA's Futuristic Technology Concept from the NASA Institute for Advanced Concepts for his ideas on quantum radar. We do have several personal points of contact with Dharman. He is the JPL mentor for our very own Priya Darshini, who's working on her PhD with David Ricketts. And David and I actually were Dharman's PhD supervisors at Carnegie Mellon. So it gives me great pleasure to introduce Dr. Dharman Arumugam.
Thank you, Dan. So thank you, everyone, for giving me some time to speak today. I'd like to introduce the topic of Rydberg-based remote sensing for Earth science. As Dan mentioned, I'm a research technologist at NASA JPL. JPL is a federally funded research lab that develops a lot of cool and exciting NASA missions. And as part of that, we are very interested in advancing in future remote sensing technologies. That's where I come in. I lead the formulation and concepts group there, and we really look at ground level advancements of remote sensing technologies that can have impact in the next decade or few decades. And so today I'd like to introduce one of the concepts that we think is very exciting, that has immediate application to Earth science, but potentially also planetary science and other areas of NASA research as well. Before I do that, I want to quickly introduce the group. So I'm part of the Applied Physics R&D group at JPL. I lead that group. It's a group of about 15 to 20 people spanning senior staff all the way down to graduate students and postdocs. And we do a lot of cool things. We try to develop sensors, as I said, from the ground up, that could be either classical or quantum in nature. And typically we apply these to a whole host of applications that are of interest to NASA, whether it be subsurface sounding, radars like we'll discuss today, or problems that are of interest to have national interest, such as pointer tracking first responders and things like that. So a whole host of different problems we work on, and our main interest is in applied physics and sensors development. So I want to start a little bit by giving a little bit of motivation in terms of why we started looking at this. So NASA does a lot of long-term planning, and part of the planning goes into a community consensus that we call the decadal survey. So every decade, NASA develops a plan for the next decade or for the next few decades through this decadal survey community survey events. These are fairly large surveys that take into account thousands of people that have background in earth science in this example. In the last decadal survey, one of the key goals that was justified by the community was STV. So we'll talk a little bit about STV here in this slide. STV is the goal of STV is to do surface topography and vegetation measurements over a very broad range of science variables, and these cover measurements that will consist of solid earth measurements, the ecosystems, climate, hydrology, and weather. So it's a very, very broad measurement of the earth system. And these are expected to be a targeted, observable, and a candidate mission in the 2030s. So NASA is very interested in developing STV-related technologies. But the big challenges with these systems is that, one, they typically heavily rely on radar remote sensing. And in order to sense the different types of variables, you need a multitude of different types of radar. So for instance, just trying to understand what optimal frequencies you would need for these type of for the type of variables that you would need in STV is quite an enormous effort on its own. For instance, if you're studying varying snow conditions or the different type of terrain types or forest structure, you would need very different bands. Even within forest structure, for example, if you're trying to penetrate perhaps the top to find out what is the height of the canopies, or you're trying to understand the volumetric biomass of the forest structure, or you're trying to understand the soil moisture underneath that supports that, or that will support the habitat, right, or the vegetation structure. All of those will require a broad array of different frequencies and bands. And so, and that's just forest structure. And when you go to the different variables, of which there are a whole host of, in order to understand how the Earth system is changing, that STV would need to address, you start realizing that there is no simple classical approach that can address that without relying on a whole multitude of sensors, which are essentially composed of multiple sources of electromagnetic radiation that covers different bands, and multiple sensors that will then detect these and do some kind of remote sensing with it through means of either radar reflectivity or something else. So how do you do it with systems that can be adaptable or tunable towards all these different bands? Is something of great interest, because NASA wants to reduce cost, essentially. One of the biggest challenges that NASA has in terms of making impactful and contributions is cost. The reason for this is because we have a cost cap that we have to live with on an annual basis, and developing more advanced sensors typically require larger cost associated with them, and in this instance, trying to do this set of variables over a global coverage would need many different types of instrumentation. So cost is a major issue. If you have systems, for example, a K-band system or an L-band system to cover a single type of variable, let's say biomass, and to do that effectively, you would need, let's say, a constellation of 10 of these. Then just imagine the number of satellites that you would need to track all the different variables with global coverage. So this is a real challenge in terms of how do we address multi-band, multi-frequency needs in compact and cost-effective systems that can fit within the NASA cost cap, so that we can monitor variables like soil moisture or biomass and study how they're changing throughout the globe as a function of time, so with some spatial temporal resolution that is needed. This is a real challenge, and this is kind of what motivated me to look at this problem from a non-classical approach. I'll start with just a high level of what Rydberg radar is all about, and that will kind of give you a big picture. So one of the things that we've known for a long time is that there's a ton of satellites out there that generate very strong signals. These are generally referred to as signals of opportunity. And over the last decade or so, there has been quite a bit of improvement in the community in terms of using these signals to do remote sensing. The first big impactful work here was a mission by NASA called Cygnus, which continues to give us good data. Cygnus used a network of GNSS satellite over a couple of decades ago when it was launched to kind of effectively do remote sensing of a number of variables, including studying hurricanes and transient events like that. And it was quite effective at doing that. Back then, a couple of decades ago, the only good collection of constellation of satellites that was out there was GNSS, and that's why we used that. But today, this has grown quite substantially, and today there's over 3,000 satellites based on the most recent calculations we have that can actually be used for remote sensing. What these satellites do, as I said, based on signals of opportunity, they're generating signals that cover a broad range of frequencies that can go typically from 100 megahertz all the way up to 22 to 24 gigahertz. And these signals are strong enough that we can use it to do remote sensing by simply receiving the field. So what this means for an instrument that NASA might launch, like Cygnus, is that it could be potentially more compact, lower power, because it doesn't have to generate strong signals, and it can consume and do remote sensing potentially over a broad spectral range. But the question is, what type of system would that be that can dynamically tune or obtain broad spectrum readouts of these fields in a way that allows you to do remote sensing? So Rydberg radar is an attempt to solve that problem using atomic detectors. And so we have a drawing on the left that shows the high level concept, not touching the atomic detectors themselves. So from the standpoint of an instrument, generally what you're trying to do is directly detect these signals from the satellite, which you can do quite easily because you have a direct line of sight. And then you're trying to detect the scattered field of the surface. And you apply a bunch of algorithms to kind of get a sense of what to kind of calibrate out the reflection coefficient, typically by doing a correlation between the direct and the indirect signal. And once you have a measure of the reflectivity or the reflection coefficients off the ground, there's a whole host of algorithms that we'll touch on later that allows you to get either interferograms or synthetic aperture radar imaging and so on, based on Doppler information, motion of the satellites, and so on. So that basis, with that basis in mind, the idea is, how can you use these atomic sensors to do this kind of broad spectral readout? Was one of the things that we were interested in maybe three years ago. One thing I'll add to this that I won't talk too much about today, but we'll chat about later at the end of the talk, is that the value of a Rydberg system like this is not so much limited to just areas where we discussed here, which is related to signals of opportunity. It is also important to bands outside 20 gigahertz, where you start being very interested in radiometer type of applications. These same systems can be simply tuned to bands between megahertz to terahertz, so you can easily and rapidly tune them to, for example, the oxygen lines or 60, 80, or 210 gigahertz, and you can easily do remote sensing there as well. So you don't have to rely, like in active radar application discussed here, where there may be signals. You can potentially retune these to bands where there are no signals and do remote sensing based on upwelling thermal emissions and so on. So there's a whole interest that is developed here is broader than just application to Rydberg radar, where there's potentially Rydberg radiometers that can be integrated as part of that instrumentation. And that's one of the big thinking behind why we think this is impactful. But in the thing that we focused on, because in life you have to focus on something that is within your grasp first, is Rydberg radar, because we think that these signals are strong. They're well above the noise thermal noise limit, or the noise limit of these detectors, as we will show. And as a result, this is something that we think we can do in just a few years. So this is fairly disruptive because it changes how you do detection of these signals. So the standard way of today of doing sensitizing these atoms to these fields is to use lasers. So you would use a probe laser and a coupling laser Typically today we do inject some RF fields and microwave fields into this. We'll talk about that more. But basically what you're trying to do is you take the atom and with one of these lasers to kind of get it out of the ground state into the first excited state, and then using a coupling laser, couple it all the way up to the Rydberg state where it's now sensitive to RF fields. So we'll go more in depth in this over the next 10 or more slides, but I want to introduce to you the concept here because it is very different than an RF or microwave or standard millimeter wave type of system. As you can see, there are no microwave or RF componentry here, right? It's just a couple of lasers. Obviously, you've got a whole bunch of optical components that go with it, but there's no RF systems or RF componentry or microwave componentry that is a part of this. As a result, this system is largely tunable because you're not limited to band-limited components that you typically would be in a classical radar system that would be composed of microwave components, mixers, and things like that. And the atoms are typically sitting in a fairly compact vapor cell. This can be on the order of a few centimeters, but it can also be sub-centimeter, and people have been advancing on more compact vapor cells as well. So principally speaking, the size and scale of this entire system is limited to your lasers and stabilization systems, which we have over the last few years really been making more compact, miniaturized, and tunable. So we think these systems are very different. They're disruptive. They have significant advantage over how we do things today because they allow broad spectrum remote sensing, and that they can potentially be very compact. And so this is kind of some of the things that excited me about this potential 3 or 4 years ago. So that's kind of the high level motivation. And with that, I'd like to kind of go into a little bit more detailed slides over the next 20 or 30 slides to give you a sense of what this technique is about. So the Rydberg atom is really an atom that we've excited to a highly excited state, where you can think about the atom for now as having a single valence electron that you have pulled very far from the core of the atom. And so the reason you're trying to do that is because, well, by the way you do it is by dumping energy into the system in a way that the atom absorbs it. And then the electron is pulled out to a very high lying orbit or high radius relative to the core. But the reason you're doing that is because classically the way to think about this is that you have a positive and negative charge from the electron in the core, and that builds up a dipole moment. So it's this dipole moment that you're trying to increase so that the atom becomes more sensitive to a microwave or RF or millimeter wave field. So the whole idea and interest behind using Rydberg atoms is that we can dump laser we can transfer energy from lasers into the atom to do exactly this. And when the atom is set up correctly, it can then be very sensitive to RF, microwave, and millimeter waves because of the large dipole nature and also because of the transitions in energy that we'll talk about later. So this is what a Rydberg atom is. It can be very large when you do this, as you expect. We're trying to make this atom as large as we can. Typically, you think about these atoms on the order of angstrom scale. But when you do this, you'll see that it can get up to about a micron in scale, and people routinely in the lab, we routinely get to close to micron scale. To give you a sense of how large that is, that's almost within an order of magnitude of what your naked eye can see. So these atoms are very, very large, but still they don't interact too much with neighboring atoms because they're still a small fraction of the interatomic distances, and so we can safely do this and use this as means of doing microwave detection. Another thing to think about is that, of course, you have to think about the quantum mechanical description of how this works. But one nice feature of Rydberg atoms is that when you pull this atoms very high into a high principal quantum number and at very great distances from the core. What the atom does is that it has a trajectory that looks like this. these lines here. And you can classically think of these trajectories in this manner. And what happens is that you think of an atom having at least some of these turning points, it spends a lot of time there. And so when you observe this atom, it almost looks like you have a circular orbit of some sort. And so it really does converge. The quantum mechanical description really does converge to an electron that orbits a circular path, at least at the high Rydberg states. And so it's easy to think of these atoms. Based on this, you can already see that we obviously would like to work with single valence electron atoms. We don't want to work with atoms that have 2 or 3 of these electrons, because the interactions between them can make things far more complicated. And so we'll chat about that. But that's the whole idea behind the Rydberg atom. If you look at the energy diagrams, which is very important to think about, these are very discrete energy levels due to quantum mechanics. And if you put a lot of energy into this will eventually ionize. Okay, and we don't want to do that. So what we try to do is ensure that you're far from the ionization levels. We don't want to get too close. Even experimentally, even when you start getting close to the ionization level, you get spontaneous ionization, and we don't want to do any of that. So typically we are getting to a high principal quantum number, but still reasonably far from the ionization thresholds. And in that regime is where the external fields can perturb this in a very stable and repeatable way. One thing to keep in mind is that almost all the physical quantities, and I put this table here because it's interesting to see, but almost all the physical quantities of the Rydberg of the atom in the Rydberg state is related to the principal quantum number. So you see this factors n floating everywhere. They're all related to the principal quantum number. So it's a very easy and nice way to think about the behavior of these atoms. As you can see, for example, the Bohr radius is changing as the principal quantum number is squared. The energy levels are changing as 1 over n squared. And then, almost, as I said, cross section as n to the 4th and so on. So it's easy to think with this atom in terms of how it scales up in terms of binding energy, radius, cross sections, and energy differences. And energy differences is actually the most important thing in terms of understanding what the sensitivity of this atom is to external fields. So we need to spend a little bit of time to talk about that. First, bear in mind that, as I said before, a lot of our interest in using these atoms require us to have these atoms, well-behaved scheme, so to speak. And typically that means we want to use single valence electrons, so there's not a lot of interactions, and excite this to a higher principal quantum number. So normally that limits us to group 1 elements. These are lithium, sodium, rubidium, cesium, and so on, because we got single valence electrons there to deal with them. So as a result, there's been a whole host of different fields, BEC and atom interferometers and so on, that have advanced lasers for these atomic species for the same reasons that I mentioned here for Rydberg remote sensing or detectors. Applies to some of these other fields, and so a lot of the lasers and stabilization systems have been matured for those atomic species as well. One thing to keep in mind, though, unlike hydrogen, where you have a degenerate form of the energy levels, when you get to all these other elements, sodium, rubidium, cesium, and so on, you get you break the degeneracy, or you lift the degeneracy in the energy levels. And so what happens is that you start having these SPDFs, as I'll show on the right, which are different orbital angular momentums. And so when you excite the atom, typically the rules that govern the behavior of the transitions do not take you from one, straight up to the next, but rather, sideways like this, like I'm drawing here. and you're typically, increasing from one principal quantum number to the other. But because the degeneracy has been lifted, you're going, changing the orbital angular momentum as well. So, you can think about orbital angular momentum for all those of you who have taken classes in spherical harmonics, for example. These are what the descriptions that you have there for orbital angular momentum is essentially related, very related to what we're speaking here about. So it's the distributions of interest that we care about in the angular space. So that's something to keep in mind, that you're typically when you're going to higher principal quantum numbers, you're also moving to the right or to the left on the your orbital angular momentums, and that's something that you have to take into account. And anytime a photon is or a transition we achieve is usually through supplying photons via a laser, and that makes this transition. So it's a very well-defined energy difference here that we have to work with. So exactly what type of energy needs to be supplied to the atom to move it from one transition to another. And then most importantly, as you can see, as you get very high in principal quantum number, the delta between these transitions get very, very small. And so what happens is that the type of frequencies related to the energy that you need to supply to make those transitions change as you get to the very high principal quantum number. And that's one of the key things in Rydberg detectors that we'll talk about in the next 2 or 3 slides. So I introduced the fact that we like to work with group 1 elements, and that is true. So if you look at some of the obvious things that we use today, rubidium atoms that we use today, rubidium and cesium are heavily used. As I said, BEC atom interferometer, also clocks, I forgot, atomic clocks frequently use either rubidium or cesium for the similar reasons that we do. But the result is that there's actually a large number of commercially available lasers to support R&D in this effort. One thing I will note is that francium, this last element here, you can't actually use it because of the half-life, but every other element here is essentially usable. And so typically we find for Rydberg applications, again, that you want to lean towards heavier atoms, and we'll talk about that a little bit more. But what it means is that most of the times we like to use cesium, although rubidium would work just fine. And another thing I want to introduce here is that the idea of how do you get to the Rydberg state. So we highlight the Rydberg state based on these 3 lines here, parallel lines. But how to get to the Rydberg state, you could use a couple of lasers, for example, an 852 nanometer and a 508, or you can use an 895 and a 494 nanometers, or you can use UV light 318 and go straight to the Rydberg state. Normally, people don't like to use UV for a large variety of reasons, including damage to components and safety and so on. And so typically, one of these other ones are often used. And the other thing I wanted to say is that there's some interesting and very useful discussions in the Doppler limits that motivate people to use lasers that are, have a closer fraction whose ratio of wavelengths approach 1. And so usually if you have options to use, for example, 852 and 508 versus a 459 and 1038, you would lean towards like an 852 and 508 type of system for those reasons. But all these lasers here that are noted on the bottom left are, for example, stuff that is out there that you can purchase. So getting to the Rydberg state is not really a challenge. Those systems exist, and you can, build that up if needed to do these experiments in the lab. One of the biggest things that we have to think about for radar-related applications is which atom to use. And what we find is that the heavier atoms are always more useful, but it's a difficult decision between cesium and rubidium. So on one hand, rubidium has been used quite a bit in the community from the beginning. But it does appear that a cesium occupies a smaller volume for the equivalent transition energies, and if you keep everything else the same, i.e. stability, laser noise, amplitude and frequency, and so on, then it does appear that cesium is the best option. Another issue with rubidium is that it has two natural isotopes, and so whereas cesium only has one. And so in cesium, when you have cesium atoms in a vapor cell, you can in principle at least interact with all the atoms, and then the energy levels imply that and the structure of the atom also slightly different, which imply that if you're low in frequency, cesium also provides, because of smaller volume, it gives you a higher proportionality of vapor pressure and more atom photon interactions, which is what you want if you're interested in kind of sensitivity. And the last thing is that the typical operating temperatures, you get a slightly lower vapor pressure relative to rubidium, which reduces the thermal velocity and reduces the Doppler background noise in these kinds of detectors. So this is kind of things that are going into a bit more detail, but it implies that we want to use heavier atoms. In this case, cesium is more useful for radar type of applications. And the last kind of technical in-depth slide that I want to cover in terms of the basics, we introduced the fact that these energy levels are quite discrete, as I said before, and that the density of these, or the separation between these, are getting smaller and smaller and smaller until when you're in the Rydberg state, that these are very dense. And so if you look at the delta energies that we also introduced in one of the first few slides, it goes as essentially 1 over n cubed, where n is the principal quantum number. So as you get to n 10 and up, this value here starts ranging going in the range of 0.1 gigahertz to about a terahertz. And so this is why this atom becomes, once it's driven to the high principal quantum number, the delta energies here being so small make it sensitive to RF fields that are in this range. And the simplest way to tune the atom to be sensitive to one band over the other is simply pushing the atom up into another principal quantum number state. And that's done by changing the laser wavelength that you supply. So as we talked about before, there are ways, for example, using UV to get straight to the Rydberg state. The problem with this is as follows. Even not bearing any of the challenges that we have with UV, getting to the Rydberg state is only half the problem, because you've sensitized the atom to RF and microwave fields, and specifically at bands depending on which principal quantum number you get to via laser tuning. That's fine. But how do you read out the perturbation of the atom due to incoming RF, microwave, millimeter wave fields? Reading out or studying the behavior of the atom is needed so that you can infer what the nature of the field is doing, how is it modulated, what type of amplitude and phase it has, and so on, right? So Rydberg remote sensing or Rydberg detectors need two things. One is sensitizing the atom by going to the Rydberg state, and the second thing is how do you read out the change in behavior when an incoming RF comes in, right? And the way that is done today, I will introduce a few other schemes, but the most common way, a common scheme that's done today is by measuring the change in the probe laser. So this is the reason that motivates us to use two lasers as opposed to one. The main basic principle here is that you're using a probe laser that drives you out to ground state. This is not a tunable. It can be a tunable laser, but it doesn't have to be widely tunable. You're trying to park this in a way so that you get exactly to the next excited state, and then you're using a coupling laser to drive that to to couple essentially to the Rydberg state. And this needs to be a tunable laser because you want to be able to hit different principal quantum numbers based on what type of bands, RF bands or microwave bands you're trying to detect. And so the way this system works is we use the probe laser as the means of readout. When RF energy comes in, it changes the state to itself, and some of the probe laser light is used to do spectroscopy of the atom itself. So the idea of being able to use one of these lasers to do spectroscopy of the atom in order to study what type of fields it is sensing is kind of the key thing in our ability to use these atoms to do remote sensing. And that's kind of so all of this is important. Another thing I will talk about here just briefly before we move on is the fact that we introduced kind of the rules where you for every laser light that you add to the system, it moves on to the right hand side of this table, which is higher orbital angular momentums. And then one thing to keep in mind is that as you get higher and higher orbital angular momentums, also the delta energies that we talked about here are also changing, and they also become more and more dense. And you can just sort of tell based on, for instance, this line here between 6 and 7, and this line here between 6 and 7. You can see that it's gone from here to here, it's gone closer. So this is another mechanism of making the atoms more sensitive to lower RF frequencies, for example, megahertz, even kilohertz, and so on. And one thing to keep in mind is that once you get to the Rydberg state, for example, here, you are now sensitive to RF fields. And as a result, you can use RF fields to make these additional transitions, no longer lasers. So really, a state-of-the-art Rydberg system today to do radar remote sensing would more than likely be composed not just of 2 lasers, but potentially even other RF sources that can help you manipulate the behavior of this atom in the Rydberg state itself. That's the high level. One other thing that is very useful to talk about is the quantum interference effect. This is very, very crucial, and we refer to it generally as electromagnetically induced transparency. The bottom line is as follows. If you have a system that looks like this, which we typically refer to as a lambda system, and if you have 2 lasers, for example, a probe and a coupler, getting to an excited state, there's 2 or more ways, or at least 2 excitation pathways to get to this excitation state. For example, if you have a very strong coupler, you can have the atom driving straight to state 3, but from natural decay and with a strong coupler, there's another excitation path this way. And so what that means is that you could have more than one excitation path. When you have 2 of these, for example, potentially there will be a phase shift in the system if everything is tuned correctly, and that phase shift can give a destructive interference. And we refer to this as generally quantum interference, but it gives something called electromagnetically induced transparency. So on resonance, where you would expect the atom to fully absorb, now the absorption goes down close to 0. So it doesn't absorb. And so when it doesn't absorb, some of the light will leak through the atoms, and that's the light that you would measure and use for sensing the perturbation of the atom. In a ladder system, which is what we typically use, the way to think about this is that you have some probe laser light that has driven the atom into state 2 out of the ground state, as we talked about before. You've got coupler that drives it to the high principal quantum number Rydberg state. Now the atom is perturbed. The perturbation of the atom based on incoming RF field changes the nature of what state 2 is. And as a result, some of the laser, the probe light can no longer interact with that because the atom has been transitioned to the Rydberg state. And so this process results in some of the probe laser light, being unabsorbed and leaking through the system. And again, you arrive at something like this, which you can then use to do spectroscopy, because as the atom is perturbed, this absorption spectrum is going to change quite substantially. And that's your method of doing spectroscopy of the atom in the Rydberg state. So that's kind of, we use this electromagnetically induced transparency phenomena to enable us to do spectroscopy of the atom so that we can study the behavior of the atom when RF and microwave field impinges onto it. So that's the high level. I think by now you kind of get the sense that we're trying to use, in the simplest case, a probe, a coupling. We read out the probe. So in a simple system like you've seen before, we've got a vapor cell with either rubidium or cesium. We have both of these lasers. Typically, they're counter-propagated in this direction because you want to reduce Doppler-related noise. Thermal motion of the atoms is what you're trying to remove as best as you can. And then when you have when it's set up correctly, you will see if you're measuring the transmission as opposed to absorption, then you would see this peak, which we refer to as electromagnetically induced transparency. When RF comes in, if it is at the right band, based on the delta energy to the next principal quantum number, as we talked about in the energy diagram, then this spectroscopy signal, if everything is nice and this is a CW type of RF signal, then you will split the EIT like this, and this is the mechanism. This always is at least the simplest mechanism of studying how to do spectroscopy with this setup in a very, very simple way to study what your amplitude of the incoming RF field is. So we talked about some of the benefits. I have some words here that talk about some of the advantages. I won't cover it, but one thing I want to talk about is the fact that this is directly samples at basically baseband, because the readout from the photodetector here of the probe laser light is going to be essentially DC to I don't know, about 10 megahertz or something like that, something low. So you don't, even if this is a terahertz signal or a 300 gigahertz millimeter wave signal that you're detecting on the waveper cell, the readout here is naturally always baseband because of the photodetector detection of the modulation of the probe light, which is what you're doing. Spectroscopy, absorption spectroscopy here measured through modulation of the probe laser light. So the readout here, even if it's a terahertz signal or 100 gigahertz signal or whatever, can be just a simple scope or a very low-cost spectrum analyzer or an ADC of any sort that is sensing baseband. So this is another one of the advantages that I maybe didn't talk about before, is that the back end of the system is very, very, very simple relative to what is typically used. And then there are a whole host of techniques that advance on this. I will just touch on this one a little bit. A few years ago, maybe 2 years ago, it was found that if you were interested in detecting weak signals, and you had laser driving the probe and then the coupling to the Rydberg state, and you had a unknown weak signal trying to drive to the next state where you can do a readout based on the probe laser light. This is a very imperfect scheme, and that a much better way would be to use a well-defined, by which I mean amplitude, phase, frequency, RF signal and microwave signal, and drive to the next transition in a very well-defined way and measure perturbations based on the well-defined transition due to incoming RF fields or microwave fields that are slightly offset relative to that signal that is driving the next resonance itself. And so these techniques are generally referred to as atom superheterodyning, and they actually make the system significantly more sensitive. I'll just give a very simple way of thinking about why they can make the system more sensitive. If you have EIT like this and you're trying to bring in RF to perturb it, you need a lot of RF to perturb it like this, like I showed a few slides ago. But if you drive that transition with the microwave at resonance, you can make it perturb. You can perturb the signal like this, or in such a way as shown in this diagram, where you can now, you have a high enough slope here, and you can be more sensitive to weak signals. And so this is the primary reason that it's sensitive to weak signal. You're addressing the atom and addressing the way the electromagnetically induced transparency is split in a way that you are more sensitive to weak RF signals. And so this whole approach that was developed 3 years ago is referred as atomic superheterodyning, and it's a massive, massive impact in making these systems more sensitive. There's a whole host of ways of how you would couple RF and microwave into these systems. I don't want to talk too much about it, but there are people working in our group. We are looking at all 4 of these, and we have supported efforts in at least 3 of these at the moment. There are ways to use ring resonators to couple and increase sensitivity. There are methods to use sub-wavelength lenses, and then there are more standard schemes like using reflectors and so on to kind of focus and direct microwave fields. We think reflectors in the end are very powerful for things like dishes that may be compact, stowed, and deployed, may be very powerful for remote sensing, because it allows you to do, it's a very broadband detector. It can go from gigahertz to hundreds of gigahertz, so doesn't limit the system in that way, but it does give you a focusing factor and allows you to use 1 or 2 cells or a few cells on the detector side as opposed to a whole array. And so I think in the end, at the moment, based on the knowledge we have, we think deployable dishes may be the way to go for how to couple RF into these cells. One thing I will just touch on a little bit is what are the line widths of the systems. So typically when you get to the high principal quantum number Rydberg state, so in the Rydberg states, the natural line widths here that you would need in an ideal world is on the order of hertz to kilohertz. So it's very, very small. Normally, that would require you to have lasers with which are very, very well tuned in terms and stabilized in terms of frequency. But fortunately, because we have to drive these Rydberg states very hard with a lot of power, we get a ton of power broadening. And power broadening then brings this line width here to the order of megahertz, which makes it so much easier then to do stabilization. So stabilizations in these systems in space would not need a high finesse cavity. You would just need like maybe a low finesse cavity or no cavity at all with some other spectroscopy based laser frequency locking systems potentially working just fine as well. And the other thing I want to talk about is that the sensitivity based on the schemes we talked about in this slide so far. You will see that it's really, you can improve the sensitivity by either increasing the coherence time or adding more atoms. And so the normal thing has been to do both, improve the equipment so you can get better coherence times and bring more atoms to the game, which allows you to further improve sensitivity. And through these type of general approaches, I'm speaking very generally here. Over the last 4 or 5 years, we've seen steady improvement in the sensitivity to the point where now it's sensitive enough for all the things that we care about relative to Rydberg radar, as we started off this conversation with. One of the in figuring out where we can make a big impact quickly, JPL NASA decided a demonstration or evaluation of the techniques relative to soil moisture would be very valuable. Soil moisture is an interesting quantity that requires you to study bands all the way from K to P band. So this is hundreds of megahertz all the way to tens of gigahertz, basically. And the reason for that is, as I said in the very beginning, they're very sensitive to different types of variables. For example, to fully understand vertical soil moisture that is impacting habitat, but also the ecosystem and the water cycle and availability of moisture to trees and plants and vegetation. You need to be able to understand precipitation in that locality, general biomass behavior, and then also soil moisture, either shallow or deep soil moisture. To do that, you need broad spectral remote sensing. So like any other significant variable in the Earth system, soil moisture does require multi-band remote sensing, and this is kind of one of the areas that we have been advancing as a means to kind of demonstrate that this Rydberg techniques can be useful. We talked about signals of opportunity. They've been around for a long time. Early systems were using GNSS. And I just want to say that the reason for that is because with GNSS, you don't need to get a copy of the signal. You have the PRN codes available. So as long as you detect the signal, you can correlate the signal with known codes, basically. But if you use other types of receivers, for example, in this mission, Snoopy, that is recently launched, JPL effort, if you detect the reflected signal, you need to get a copy of it, as we talked about, which is the same for Rydberg techniques. And so because you don't know what data modulation schemes are what type of codes are being used or schemes are being used, so you need to detect a copy in order to decorrelate the signals. And so that's the way this would work. Once you've been able to get the direct and indirect signals, and once you've done correlations, then you can do radar type processing techniques such as delayed Doppler mapping, synthetic aperture radar processing, or whatever other approach you want to think about. But essentially, the simplest thing to do is typically resolve this based on constant Doppler lines and delay lines, which you can do based on just something like delayed Doppler processing that improves the resolution. And then once you have a more improved resolution, you can then do processing to go from the reflection coefficients to variables like soil moisture. That's kind of the high level of how these systems would be operated. There's been a whole study at JPL that I won't go into too much detail to look at all the big networks of satellites that we can potentially use early on in soil moisture. Most of the lower frequency sub-gigahertz, these are military signals, where there's a huge network of, for example, satellites of ORBCOMM in LEO, MEOS in GEO, and so on that we could use. The military uses for communications. And then, GNSS, there's many GNSS networks. Then there's XM radio and a lot of TV satellites and so on at the very high end of the spectrum. So we want to be able to try to use all of these. Most of the ground experiments that we will do early on are going to be without Doppler information, just because the systems are going to be on the ground. There's not a lot of motion. But eventually, when you get to airborne and spaceborne, then you'll get back that Doppler information, and you can do things like delayed Doppler mapping and so on. A quick note on the nature of scattering. In signal of opportunity techniques, the best thing to do, because some of these signals are still reasonably weak, is to do what's known as a forward scattering. So unlike back scattering, which goes like that, in forward scattering mode, you're trying to get the specular scattering, you're trying to excite and see the specular scattering regime. One thing to keep in mind is that when you look at the specular scattering regime, there are both coherent and non-coherent components, and the coherent components goes like that, which means it's lower loss. So typically what we find in specular scattering regime, if you look at the scattering coefficients, they can be in some instances greater than 0 dB. So because of the nature of specular scattering and due to the nature of propagation dependence, essentially. And then once you detect the signal, most of the signals have a high modulation rate, and so it has a high instantaneous bandwidth or signal bandwidth. And if you integrate that for a certain amount of time, you can get what's known as processing gain. And so these processing gains can be fairly high. They can be on the order of 30 or even up to 40 dB of gain in some cases, all right? And if you're in the ground static, typically you're going to have resolutions that are not dependent on integration time, of course, or velocity. So these will result in kilometer or hundreds of meters type of resolution typically. But once you're able to get an airborne system or a spaceborne system and integrate for a reasonable amount of time, depending on the velocity, what studies have shown that you can get down to meter level, few meters type of resolution, spatial resolution on the ground. So we anticipate the ground-based experiments are not going to have lots of resolution, of course, for all the reasons we talked about. In airborne systems, you can get a lot of resolutions, and it can probably be sub 10 meters at the various bands that we talked about based on our study. And signal to noise, we don't anticipate that to be an issue. However, there has been a lot of studies to kind of look at what exactly is signal to noise based on all these different satellite networks and based on integration time here. And what we find is that, for most reasonable integration times that are used in signal of opportunity, which are millisecond scale type of integration is what typically used. There's in most cases more than enough sensitivity when you couple this with a dish reflector or something like that. So the thinking is at the moment that these Rydberg techniques will need to use some means of focusing into the vapor cell. The standard way that seems to work really well is a deployable dish reflector of some sort. It could be a parabolic, or it could be something like a parabolic. And that will get you to the sufficient signal to noise of the entire system in order to detect all these signals that we talked about before, going from the 100 megahertz regime up to about 22 gigahertz, spanning over thousands of satellites and over at least 10 to 15 networks of constellations, essentially. There has been a lot of study to kind of get a sense of what is the signal to noise globally. I don't want to talk too much about this. These by themselves are quite involved. Unfortunately, we have to do this to kind of understand what the spatial coverage is. Perhaps this is a talk on its own, but what we find is that generally for where there is coverage from these networks, that we can get enough signal to noise to do remote sensing. And so people in my group have also developed a lot of end-to-end modeling where we kind of study the behavior of satellite motion and perturbations of the fields, and then specular response of rough surfaces, based on certain type of gentle undulations that we might expect in some of the areas where we want to do remote sensing for soil moisture. And then with modeling the Rydberg detectors, which is by itself an entire effort that we won't be able to touch on today because it's very, very involved. How do you model the behavior of the Rydberg detector in its full form requires solving Hamiltonians and Lindbladians and doing this in nonlinear ways, and then developing approximations so you can get some level of linearity as you would see in your measurements. Is a whole topic on its own and would require a whole talk on its own, maybe someday. But we've been able to do that at JPL. So we got end-to-end models basically. And this is an example of simulated data. As you can see, it's baseband because of the readout of the detector, where we are simulating really what the signals would look like in a receiver in space. So there's been a lot of efforts in modeling at JPL. We've developed some concepts in terms of how this would work. So we have a sense of what the systems would look like in a CubeSat, for example. This ongoing effort to develop more compact laser systems. We need multiple polarizations. The simplest way right now to do that is to have two vapor cells and use the same lasers to drive them both, and have these systems, these detectors, be top facing and bottom facing, so you can get the direct and indirect signal with the assumption that this satellite will be in LEO. Most of the networks that we're interested in, satellite networks we would use as sources, are going to be in GEO. So just to give you a sense, so this architecture is a couple years old, and a lot of things have changed since then, but essentially it's the same, but it's being improved based on what our needs is and where we think we can go in 2 or 3 years, basically. So with that few minutes, I want to talk about, in the next few minutes, I want to kind of wrap up and talk about systems and experiments we've been using. So our probe lasers are that we've developed or acquired are in the range of 852 nanometers. Our coupler are 510. Our system is basically going to experiments. We have the probe, and then we have the coupler. There's some switches and wave meters and so on to kind of measure these wavelengths, get its course. But then the probe laser is then locked via saturation spectroscopy, and the coupler through a high finesse reference cable. You don't need the high finesse, but in the laboratory environment, it must make sense to do that. Our cavity really has a finesse about 20K, so I don't know if you really call it a high finesse, maybe medium. And we use pound river Hall, which is a well-known textbook kind of approach to do laser stabilization. Similar type of laser stabilization is applied here on the top for the probe, but that is using a saturation spectroscopy. Typically, as we kind of introduced before, you need a few nanometers of tuning range on the coupling laser and a lot of power because you're trying to go to the high principal point number. On the probe, on the other hand, you need very low power, and you don't need much of a tuning range. So I'll just leave it at that level. There's a whole host of other things that in the lab you would have to check out, things like Rabi frequencies, which we commonly on a daily basis calculate out and make sure we can hit. Because those tell you exactly the behavior of the atom that you as you're transitioning it. But so the only thing I think that's worthwhile to point out here is that typically, in the Rabi sense, is typically that the probe is going to be weakly coupled, and that the coupler is going to be strongly coupled, which is in a sense also pointing towards why you need quite a bit more power in your coupling laser, but very weak in your probe laser. This is a standard experiment that we have. We have a cesium cell. We like to use TEM cells, which is a transverse electromagnetic cell. It's a simple way of injecting fields. We're not at the point, of course, now where we have satellites and things like that. We're in the lab doing a lot of experiments. And so this is kind of general setup. We have the probe laser, the coupling laser. We need to do some attenuation controlling and beam displacements here. Our approach has been to use a beam displacer. It worked out really well for us, where we have two probe laser lights. We interact the coupler with one, and we use the other one as a reference, and then we do a balanced kind of detection. I don't know if it's the best way to do it, but it works really well for us. And I think at least there's one other group I think in China that is making very good progress with this type of approach as well. Just a quick view of what the probe laser looks like. You got a laser diode, which is where you want to spend the most of your time. And we do also have a tapered amplifier, but don't need that. And then you'll do some isolation, and then you have an output beam. And here's what the coupling laser looks like. Coupling laser looks a lot more complicated because we don't know how to do 510 nanometer lasers today very well as a diode. So we do 1020, and then we have to taper amplifier here is very important. And then we have to do this whole thing with EOM, pound river Hall of the via cavity to kind of stabilize the mode of this, but also to get second harmonic generation of this 1020 so that we can get to 510. And so as a result, the coupling laser is quite more sophisticated, sensitive, and requires probably like weekly checkups kind of thing to make sure that it's working. So these things are, we take it apart often just to give you a sense, and it's like a Ferrari, you got to fine tune things. So there's a lot of work that needs to be done to kind of get this to a point where it can be compact and space qualified, of course. There's a slide on saturation spectroscopy. I don't want to spend too much time other than to mention that what we're trying to do in terms of locking the probe is to excite the hyperfine structure of the atom. And then once you're able to do that, you want to modulate the probe and lock to this hyperfine structure. And that's how you kind of stabilize the frequency of the probe laser light by locking it to the hyperfine structure of in this case, cesium atom. And so we in the D2 transition. So this is what we do in order to lock the probe laser. There's nothing really new about this approach because it's been used in labs all over the world. So if you're interested in learning more about it, read more about it. And then for the coupling laser, we use pound river Hall. Again, this was invented by Rydberg, I think, in the 80s, before I was born. So this has been around for a long time as well. And I don't know if it should be a textbook thing, but I don't know if any textbook that really goes into great detail. Although there's a lot of articles online that discusses and is routinely used. It's again another stabilization system, but in this case, you use a high fitness and very well controlled optical cavity, and there's a whole host of systems that goes into stabilizing just the cavity in terms of pressure and temperature. But when that's done, then you have a very nice cavity that you can use to lock your laser to, and you can get great frequency stabilization from that goes down to hertz. Experiments like LIGO go down to millihertz or better. In our case, we only need like kilohertz or even worse. This is a very simple setup of how you might do things in the lab on a compact table. You got vapor cells and then all the stuff that we talked about before. Here's the photodetector. Lasers are coming in here and in here essentially. So JPL has been advancing on a number of different experiments to kind of advance toward outside of first do a laboratory experiment, study how the behavior of the systems with the transverse electromagnetic cells, progressing towards field experiments. Right now, we're trying to advance to outside the lab where we can do a combination of classical and quantum detectors. So on the ground, we would have a classical system detecting the signals from the satellites, a quantum system measuring the reflections off the ground. So you have the system that's pointed downwards essentially, and to the correlations of that, you can infer a lot about the behavior of the quantum systems relative to doing remote sensing. And then in the second part of this year, we're going to do a full quantum approach with 2 detectors to look at the direct signal and indirect signal. So there's ongoing work to kind of do all of that. In the lab, we kind of have systems that, as you can see with the TEM cell here, and you see the vapor cell that is lighting up in green because of the green laser light from the 510 nanometer light that is coming in this direction, and the probe is coming in this direction. You don't see the probe because it's weak. So this is kind of the systems we have in the lab. We've got 2 separate quantum optics laboratories that we've developed in my lab, in my group. And there's a lot of interesting, cool experiments that are ongoing. One of which is Rydberg related. So here we kind of use a TEM cell to kind of make things simple for us and pipe in RF signals right now. So we're not quite at the point where these systems are compact and be taken out of the lab, but we can easily pipe in signals from outside. And so there's been a lot of analysis, such as this data collected showing that, even when you get to 30 or so or 40 dB below your pre-correlation SNR, you can pull out modulated signals from there, which is what we would need to do in space. And these have been shown to be quite feasible in the lab based on collecting signals, modulated working with modulated signals and correlating them with known copies of those signals. So things seem to be working quite well. We've also started doing a lot of experiments with these systems by piping in signals from, soil moisture type of experiments, and we can, with calibrated soil moisture, we can see that, relative to scattering coefficient, relative to soil moisture, we get a very good relationship measured out with this Rydberg atoms. For instance, in this case, studying volumetric soil moisture content at 2.3 gigahertz, which is an XM satellite signal band that we would use. So a lot of exciting, cool work going on here and in the lab, and things are moving quite nicely towards where we think we can potentially in the next year or two start thinking about airborne type of demonstrations. But there's a lot of work between now and then, so we're very busy in the lab. I think this is a slide that I reused. I just wanted to state that I think likely where we are now suggests that we will be relying on some kind of deployable dish or reflector of some sort in order to kind of focus into the cell, as opposed to using antennas like this, point antennas that are coupling. Will be, you'll have a cell that you're focusing electromagnetic radiation into. So I think in the interest of time, I'm going to skip over through some of the other efforts that are kind of related to this. And this, I just stop here and show you an example of some of the ongoing work with reflectors to study that we can indeed get the type of focusing we want. A lot of work is still needed to kind of advance to the point where we can have these Rydberg systems outside. The simplest way to do that right now that we think is to, you can either somehow find a way to fiber couple your system from 100 meters away into the lab, or you can fiber couple the vapor cell out, which is also another option, and that's an option that we're developing on right now, so that you can leave the quantum optics setup and lasers and stabilization systems in the lab, but just have your vapor cell fiber couple out. So that's sort of ongoing work to get to the point where we can do these kinds of things. Stay tuned. Maybe we'll have more interesting and exciting things to add to this discussion in the next year. I just want to kind of quickly state there's a bunch of different studies only on the Earth science ongoing right now. And my group is also starting to advance on the planetary science applications, a lot of interesting applications there. Where we are right now is that we are trying to advance ground-based demonstrations. As you can see from the last few slides, we're doing quite well on that, I should state. We think in the next fiscal year in 25, that we want to target some type of airborne demonstration. So we have efforts ongoing to kind of study whether a ballooning type of approach could work for us. And then long-term, our plan is basically to have an experiment in space in the 27-28 timeframe. It looks like a long time for some of you in grad school, but given where we are in this, in quantum sensors, this is pretty fast in terms of getting into space and to doing an experiment in space. So we're trying to move as quickly as we can. There's a whole bunch of different applications outside of the ones I spoke about that my group is attempting to advance. There's way too many than what we can do with just the people that we have. But one area that interests me a lot is broadband radiometers. Today, missions like Juno use radiometers that are the size of a small building to cover 6 bands. So we think we can cover 1,000 bands with something the size of my laptop. So I think we have a lot of interest there to advance the state-of-art radiometers, and we're taking it quite seriously, and we're spending as much time as we can afford to kind of study how these systems will work in radiometers as well. So more to come on that. And then in a quick summary, I think there's a lot of interest in Rydberg remote sensing. I think we are the first group to kind of, first also think about it, but start doing some initial experiments and promoting the concept, and maybe even some of the first, I would say the first experiments came out from our group. And there's a whole host of different activities and support now in advancing these. We think it has massive impact to radars and radiometers that are very broad spectrum and compact and tunable, addressing all the needs of NASA in the next few decades. And we're leading an active collaboration many of my good friends and colleagues at NIST and ARL and others are part of this collaboration. We are, always looking for people that can support that, and we're always looking for postdocs. So that's the other thing I wanted to mention. And with that, I think I will end and open up for questions. Spurs, back to you.
All right. Yeah, thank you very much. That was a great presentation. And I was very interested to see also the progression as you moved into the more experimental setups later on. So that was very, very good. We actually already have some questions lined up here in the Q&A box, so I'll read them out to you. The first question is from Neil, who says, how much dB of SNR gain is obtained by using a Rydberg sensor as compared to conventional dipole antenna receiver?
That's a very good question. You don't get a significant gain in terms of SNR. In fact, the signal to noise suggests that we are on the order of at best. So I don't think with Rydberg techniques you're going to get improvements in signal to noise over classical systems. Not quite yet. In a few years, maybe you can improve over them. There are some new and exciting schemes that beat the limit of sensitivity, but right now I think we don't beat the sensitivity limit of what you can get from classical systems, but you can get the broad spectral tunability without the limitations that the classical systems have, which I mentioned many of them, including the RF component trees that you would have to use in classical systems that you don't need to in these quantum systems. And you can tune the systems within, well, rapidly tune it, I should say, between megahertz and terahertz, for example, which is impossible with classical systems. So there's a lot of, and then the compact schemes that you can develop this in, suggest that they can be very, very small instruments that can tune throughout this band. So there's a lot of interesting, valuable improvements, but improving the signal to noise or sensitivity or what classical systems can do is not one of them. There are, however, some very recent experiments showing that you indeed can improve the sensitivity quite significantly. These are not, these are too early to speak about, but I will give you just a quick sense of why or how this works. So basically, the biggest problem with sensitivity in Rydberg systems, and the reason you cannot overcome what classical systems can do in terms of sensitivity, is because the probe laser light is what is used for the readout. So today, you read out the probe laser light, and that readout is what's being used. So any noise that your probe laser light has in terms of amplitude and frequency is transitioned into your readout, and there's no way to simply remove it. So we've developed this very complicated and fancy quantum detector, but the readout mechanism is very, very limited. Okay, this is the problem in Rydberg techniques today. And so if you can solve this problem, you win, because now you're dependent on just the sensitivity of the atom, which is very, very sensitive. The quantum limit is very sensitive relative to classical detectors. But the problem is you can't get the quantum limit easily because you're reading out a probe laser light, and people don't know how to make very low noise probe lasers. So that's the big problem. There are some new, very, very recent, just in the order of months of how to solve this problem. I don't want to go into too much detail, but it involves Rydberg spectroscopy. It involves fluorescence spectroscopy techniques through wave mixing. So instead of trying to read out the probe laser light, the approach that has been recently developed is to, once you get to the Rydberg state, you use microwaves, as you know, to get to the next state, and this is the microwaves you want to sense. Instead of trying to read out in the probe laser light, you decouple this with another laser, with a third laser. And the decoupling gets close enough to the first excited state that the wave mixing and the system is tuned in such a way that this wave mixing behavior, due to the decay of the atoms and so on, naturally excite a fluorescent signal here, and in a unidirectional way. And this fluorescent signal is excited as part of the energy balance equation, or so to speak, that you have here in terms of the drawing. And this fluorescent signal basically very, very efficiently converts between the microwave and has a very strong coupling coefficient between the microwave signal, and as a result, it's not limited to probe laser because you're not trying to detect the probe laser. You're just trying to detect the signal. So if there's no microwave, there's no fluorescence, and when there is microwave, there is fluorescence, and it scales in a very unique way. These techniques are generally, for lack of better terms, because these are very, very new, are called just wave mixing. Okay, and these wave mixing techniques basically used with fluorescence spectroscopy is going to beat the limit of sensitivity in classical system, which is the only thing that we don't beat right now. And so you are probably in a year or so, I think we will have a lot of groups, well, at least 1 or 2 groups globally experimenting with this. Right now, this is very new stuff. So stay tuned. This is a rapidly evolving field, I should say. But outside of sensitivity, beating the sensitivity limit of classical systems, everything else, I think we have already shown that there's substantial improvement. So next question.
Fantastic. Yeah, thank you. So Priya, who I know you collaborate with, has entered a few questions along with a very enthusiastic thank you for the good presentation. I'll start with one of them, and I know we're kind of a little bit short on time, so we'll start with one, and then we'll kind of see the time that we have afterwards. But one of the ones that I thought was also on my mind was if you could comment on the effect of ambient conditions, temperature, for example, working in a cold versus a warm environment, how that might affect atomic collisions, the glass cell, especially now as you're moving from ground-based demonstrations to airborne demonstrations. Can you maybe comment a little bit on those effects?
Yeah, certainly. So temperature in the lab, we find that changes on the order of about 10 to 15 degrees Fahrenheit does not impact our sensitivity or readout significantly. So basically, it's not very sensitive. You don't need stabilizations better than a few degrees, basically. And so generally speaking, when you get to outside environments, meaning outside the lab in outdoor environments, you want to stabilize the temperature, generally speaking, so they don't have large changes of 20 or 30 degrees having significant impact during the course of the day. The standard way to do that today is to drive it to a higher temperature and maintain it, because there's a lot of systems out there already that we've matured through various different needs in the community to do temperature stabilization. So they're all over the place, basically. Temperature stabilization is something we know how to do really well. And so I think if you once you transition out of the lab, as you can see in the lab, we're not using any kind of temperature stabilization of the cell itself. When you get outside, then you need to do some kind of temperature stabilization. And so we'll have to use the systems that are out there, but they're easily attainable and they're available to use. And so we would use those. The other thing I wanted to state that's related to that is that when you get to space, all these problems go away. Because in space, LEO, for example, what you will see is that the temperature is very, very, fixed and very close to, you can get it very close to room temperature and within very good stabilization. And so that's commonly seen and commonly done for many of our space applications in LEO. And we anticipate that not to be the problem. A lot of the problems, it's kind of funny, but a lot of the problems you see in the lab, temperature, vibration, all these things go away when you go to LEO. So that's another thing to keep in mind.
Interesting. I didn't expect that, actually. That's very, very convenient. So maybe one more question here, also from Priya. She asked if you could comment on the sensitivity and signal to noise ratio with respect to the Rydberg state. She commented on how higher Rydberg states will probably have longer lifetimes, which could affect, for example, the bandwidth of the signals. Could you maybe comment a little bit on that trade-off, what kind of relationship there might be?
Yes, and I think one of the things that is a bit confusing is that a lot of the work that has been published is on resonant detection. And so what that means is that you're driving the state on resonance, and you're trying to do readout of signal on resonance. On resonance readout typically is going to have a fairly rapid bandwidth drop off, and so these systems can naturally have a low bandwidth as a result. Fortunately, if you go off resonant, meaning your resonance is, let's say 10 gigahertz, but you collect data at 2 gigahertz, you start getting natural increases in the bandwidth. And the reason for that is because you're no longer using, you're starting to use the atomic polarizability of the atom. And that can be more forgiving in terms of instantaneous bandwidth. And so naturally, I think you can get the instantaneous bandwidth of a few hundred megahertz, but there's not been a lot of published experimental work because people have been very focused on doing on-resonant stuff to improve the sensitivity. So I think when we solve the problems related to sensitivity using fluorescence spectroscopy techniques, we probably will also start looking at how to do off-resonant type of experimentation or measurements to increase the bandwidth. Right now in the lab, even when you're on resonance, you can typically get bandwidth on the order of about 10 megahertz generally. That can be generally seen in terms of instantaneous bandwidth. To get more than 10 megahertz, as I said, you need to go off resonance, and you can get to a few hundred megahertz, but it's very difficult to get into gigahertz type of bandwidth with these systems. So that's not what we want to do. Rather, I think the approach would be you live with a reasonably narrow bandwidth, but tune rapidly, which is how you would capture a large spectrum. So the way I think about it is that these Rydberg techniques are probably not going to be broad in terms of instantaneous bandwidth, but they will be broad in terms of spectral coverage, basically. And so that's one way to think about it. Now, having said that, my friends in New Zealand have been advancing broad instantaneous bandwidth systems through arraying. And they have been quite successful at doing it. And the way they do this is actually within one vapor cell, there's a few centimeters long. Your excitation is only millimeter scale. So you have plenty of other space in even a few centimeters to use. And they use micromirrors and things like that to excite different volumes in different portions of that volume in that small vapor cell to make unique Rydberg transitions in there. And they can do that quite neatly in a way that they can stack up the instantaneous bandwidth right beside each other by driving it at different frequencies and increase the instantaneous bandwidth. So I think even if you want to take the traditional approach to do Rydberg detection and increase the instantaneous bandwidth, there are ways to do it without changing the system too much. But by itself, with a single transition in the most classical way, it's going to have bandwidth limitations between 10 and about 100 megahertz, depending on whether you're on or off resonance.
Fantastic. Thank you. All right. Well, I think this brings us to the end of our scheduled time, and I see some folks starting to log off. I know some folks have class right after this. So I just want to thank you one more time for the very, very interesting talk and also all the perspectives during the Q&A afterwards. Dan, before we go, was there anything that you wanted to add?
Yeah, unmute myself. Yeah. No, it was a very interesting talk. It's great to learn about it and appreciate it very much, Darmin.
Thank you. Thanks for the invite, and I look forward to meeting all of you in person at some point.
Absolutely. We'd be happy to have you here sometime if you are able to make it out here in person.
Yeah. Thanks, Spiros, for organizing and coordinating. Thanks for all your help.
Not a problem. Thanks for accepting, and thanks for the great talk again.
And for all the students that are still online, if you'd like to visit the lab or collaborate in any way or join the group, we have plenty of opportunities, and we're looking for people to bring their diverse experiences and exposure in ways that can contribute. So any ideas on how we can collaborate is we're excited to build and improve our collaboration. So we're very interested in that. We have a lot of postdoc openings as well. Something to keep in mind. Thanks, Spiros.
Definitely. Yeah, no problem at all. And I wish everyone a good weekend.
Thank you. Take care.
See you.
Bye.
Bye-bye.
Bye. Bye.